Okay, this video this is about second PUC physics practicals. This is different from the usual live videos about NEET NCERT revision. This is a little special, and I'm going to be explaining a few experiments of second PUC physics practicals, and these are resistivity of the material of wire, of any unknown wire. Second one is resistance per unit length of wire. Third one is figure of merit of galvanometer. Fourth one is galvanometer to voltmeter conversion. And fifth one is frequency of alternating current. These 5 experiments I am going to be explaining in this video. Now coming to the first experiment. The first experiment is resistance or resistivity of wire, or the full name here, resistivity of the material of wire, of material of wire. Here, resistivity of material of wire. First we are going to talk about the circuit diagram. It is very simple. Actually, in the 5 experiments, the first experiment and the second experiment, the circuit diagram for both of these is exactly the same. The circuit diagram is first the battery connected to a switch, then a rheostat, ammeter, our resistance wire. Our wire is represented here. The resistance of our wire is R, and we connect a voltmeter, and we know how to connect a voltmeter. We connect a voltmeter in parallel. We connect an ammeter in series. Now this connection, we take it and keep it here. We do not directly connect. This is a rheostat. Rheostat is a variable resistant, and marking here, this is a battery, this is a switch, this is an ammeter, this is a voltmeter, and this is the unknown wire resistance. Now this is battery, this is switch, K is for switch, A is for ammeter, R is for the unknown resistance, V is for voltmeter, then RH is for rheostat. Rheostat is variable resistant. First of all, why do we need to use variable resistance in these circuits? Is because we use variable resistance to adjust the voltage passing through the circuit. To adjust the voltage passing through the circuit. RH, that is rheostat, used to adjust voltage and current through the circuit. Okay, how do we know that rheostat is known as variable resistance? How do we adjust voltage and current through the circuit using a rheostat? We know Ohm's law. Voltage is directly proportional to current, and V, which is equals to IR, where R is a constant known as resistance, and V by I, which is equals to R. So when we adjust resistance, we can adjust both voltage and current in a circuit. So an easier way, one of the ways in controlling the voltage and potential and current in a circuit is by using or connecting a rheostat. This whole setup, which we will see in many of our electrical circuits in the next experiment as well. The main reason for the use of a rheostat connected to a battery is to vary the current. Okay, let's continue. That is not a part of the experiment, but just this is a theoretical explanation of why we need to use a rheostat here. Okay, that is a circuit diagram. Now what is needed here? We need radius of this wire we are finding. This is the resistance of unknown material or unknown wire. This is basically represented as a resistance, but it is basically just a wire. Now if it is a wire, it will have some radius, and this radius will be given for us. We don't need to calculate it. It will be given as r equals some meter. I'm not going to use the exact calculation. This is just for understanding sake. Now the second one is length of the wire. Length of the wire will sometimes be given and sometimes will not be given for this experiment. Length of the unknown wire, unknown material wire, which we need to measure using a meter scale, or it might just be given. I'm not too sure. Let's continue. The first thing, this is a circuit diagram. As for explaining the circuit diagram, a battery is connected to a switch, then a rheostat. This whole setup is for controlling adjusting the voltage and current in a circuit. And we know ammeter is connected in series in a circuit because current is constant in series only. So we connect ammeter in series, and we are going to measure potential difference across the unknown wire. So we are going to connect a voltmeter representing V in parallel around this resistance unknown wire. That is circuit diagram. Now let's see the aim of this experiment. Very simple. Aim of the experiment is to determine resistance of the given wire using Ohm's law, and hence find resistivity of the wire. To determine, very simple here, we first determine the resistance of the wire, then using that resistance we are going to find a resistivity of the wire. The apparatus used, first the wire, the unknown resistance wire, battery, voltmeter and ammeter, plug key, and rheostat and meter scale. Why we need these? Wire, battery, voltmeter, ammeter, plug key are part of the circuit along with rheostat. Meter scale we need in case we need to measure the length of the wire, which was not given to us. Okay, that's with the apparatus. Now principle, it is Ohm's law. For the first and second experiment, the principle is Ohm's law. Ohm's law basically states that the electric current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor at constant temperature and pressure. This is the principle, very simple, already known. I is directly proportional to V, and I, which is equals to, I mean, V, which is equals to IR. This is the main formula of Ohm's law. It is good to remember this, and it's almost very hard to forget this. Now, formulas in this experiment are basically just finding the first formula is R, which is equals to V by I. From this equation itself, we can derive R, which is equals to V by I, where R is the resistance of the wire. V is voltage or potential. I is current. Now, the second formula for this experiment is resistivity of the material, which is denoted by rho. Rho, which is equals to RA by L, which can also be written as R 4 pi R square. I mean, not 4 pi R square, pi R square, pi R square by L, which can be capital L or small l, where L is the length of the wire, length, radius of the wire. This is resistance of the wire. As for how we got this formula, R, which is equals to, this is the main formula, that is not this one, rho, which is equals to R pi R square by L. As for how we got this formula, pi R square is basically just area of a circle, area of cross section of the wire. How we got this formula? R is directly proportional to length. R is directly proportional to, I mean, inversely proportional to area of cross section. Combining that, we will get R is directly proportional to L by A, and introducing a constant, R is directly proportional to rho L by A, where rho is known as resistivity, and shifting it, we will get this equation, and we know the area of the cross section of wire, which is pi R square, so we substitute it here. So both the formulas are easy to derive and easy to remember. Now coming to the procedure of the experiment. First step, make the connections as seen in the circuit. We adjust the rheostat. I told you, right, like the rheostat is used to adjust the voltage and potential, and we will make a tabular column of different values of I and V, out of which we will calculate the resistance. Adjust the rheostat for a particular value of current. Then the corresponding, we just adjust it, we turn on the battery, we close the plug or like turn on the switch, and we adjust the rheostat for some current like 2 amperes. Like we connected the ampere in the circuit here in the circuit diagram, we connected an ampere. So after we connected everything and we close the plug key, let's assume we adjust the rheostat to show some 2 amperes in the ammeter, and if it is showing some 2 amperes in the ammeter, there should be some value shown in the voltmeter as well. It won't be 2 volt or anything like that. It might be, but depending on that, on this 2 ampere, there will be some value or noting in the or reading in the voltmeter. This reading is noted down. Both these readings, for example 2 ampere, here 2 volt or 3 volt, both these values are noted down for the first time. Next, second reading, we adjust the rheostat that this will show 3 ampere. Now here it will show some other value, some other x volt. This voltage and this current we note down in our tabular column. Then corresponding I and potential readings are noted down. Next, that's all. They will be tabulated. We don't need that step. I'll mention the tabular column. Tabular column will be something like this. Here trial number 1, 2, 3, I in ampere, voltage in volt, resistance which is equals to V by I. For certain voltage here readings, we will calculate V by I resistance in ohms. All the values we will take and we will note down and calculate the R value. We will get 3 different R values, or actually technically we should get, if our readings are exactly accurate, there is no error, all the R values should be same. For all these trials we should get the same R value, but because there might be small errors which are impossible to avoid in human calculation, so we will get slightly different R values in all 3 trials. So if we get slightly different values, we find out the average R, which is equals to R1 plus R2 plus R3 by 3. This is the average. But since our goal is not to find resistance but resistivity of the wire, we want to find the resistivity of the wire. So we find rho 1, which is equals to pi r square R1 by L, rho 2, which is equals to pi r square R2 by L, and rho 3, which is equals to pi r square R3 by L. Now all these we calculate, and rho average we will get it as rho 1 plus rho 2 plus rho 3 by 3. Now result, we write resistivity of material of wire rho, which is equals to some value ohm meter. Ohm meter is the unit of resistivity. That's about the first experiment. Coming to the second experiment, which has the same circuit diagram. The second experiment is resistance per unit length of the wire. Here as well, we will be given an unknown wire and we need to find the resistance per unit length of that wire. Here, the method is a little different. Here we don't use the Ohm's law directly, but we depend on plotting of graph and then calculation. Let's see circuit diagram and graph first. Circuit diagram is same as the previous one. So let's draw the circuit diagram. Battery, switch, rheostat, ammeter, our resistance wire, battery, switch, ammeter, plus minus, resistance, and rheostat. Everything is here, exactly the same thing as the previous diagram. And the graph, a sample graph, which we need to draw before itself, or maybe not. I'm drawing a sample graph, but if we do the calculations, we will get the same graph as this. This is I in ampere, current I meaning current, V in volt, V meaning potential. And we identify the slope of this curve. Okay, I'll write the equation here. Since this is the y-axis, this is the x-axis, the equation, if we compare it to y equals mx plus c, the equation we should get is I, which is equals to mv plus c, and c, the y-intercept, it is starting from origin, so we can consider it as 0. Then we will get I, which is equals to m into v. M is the slope, I is current, V is voltage or potential. From this, we can say that I by V, which is equals to M, and from this equation, we can say that V by I, which is equals to M. I mean, not M, V by I, which is equals to 1 by M. Just reciprocal this equation. Why we need to write it as V by I is, if we remember the Ohm's law states that V is directly proportional to I, which is equals to IR, and V by I, which is equals to R. So V by I, which is equals to 1 by M, which is equals to R. So R, which is equals to 1 by M. Okay, that is about the resistance. As for how we should calculate slope, if we assume this as an ABC, just connecting two random points, let's assume I got some readings here. Now connecting these random points, we will get this triangle here. Now slope, which is equals to dy by dx, or y2 minus y1 by x2 minus x1. That is basically from our ABC, we will get it as AB by BC. Our slope is AB by BC, and from this we will get 1 by M, which is equals to resistance. This is not supposed to be explained here, but I explained it because one of our formulas shows this R equals 1 by M. It is not mentioned how we got it, so we got it from this, and how we should calculate slope also, I mentioned it here. Now we only have two diagrams here. In our first experiment, we only have the circuit diagram. We should mention BA is battery. I'm not writing it to not waste time. but it is mandatory to write BA, which is battery, K, which is switch, and so on. In our first experiment, we only have one diagram. In our second experiment, we have two diagrams. One is our circuit diagram and second is the graph. This is a sample graph. We should take a proper graph sheet and plot the actual graph, but we will get a graph similar to this. Now coming to the given values, actually there is nothing given here. They asked us to find resistance per unit length, which is nothing but we find resistance, then we find length, and we divide resistance by length. This is what we need to find. This is the, we should find this one to find. So resistance, how we need to find, I explained here. Resistance, we take a graph of IV values. How we should find this IV graph? In our previous experiment, I showed how we should adjust the rheostat values. If we adjust one value, like example, without adjusting, after we start the battery or turn on the switch or close the switch or plug key, let's assume this shows 1 ampere, then the corresponding value of, in voltmeter, it shows some 1 volt. These both are noted down. After slightly adjusting the rheostat, let's assume this shows 2 ampere, and because the current is changing, potential will also change. Let's assume this will show, it's just an assumption, not real values, 2 volt. These both values, and more trials are taken, and all these values are taken down in a tabular column, and from that we plot this graph, and from the graph we will get slope, which is AB by BC, and our formula R, which is equals to 1 by M. We will get resistance. Length of the wire we calculate using a meter scale. Okay, we need to calculate length of wire using meter scale, or which might be given. Tabular column. Here we do not use Ohm's law to calculate resistance. We use the graph of the experiment. We use the graph of the experiment. We use the graph of the experiment to find the resistance. Trial number, I in ampere, V in volt. We take some 5 to 6 readings. We plot the graph. We find the slope and we calculate resistance. I'll just write the procedure once, like not procedure, the AM steps and so on. AM, which is very simple to remember. AM, which is to determine resistance per unit length of a given wire by plotting a graph of current versus potential. That is the aim. Apparatus, I don't probably need to mention, it is the same as the previous experiment. Apparatus is a wire of unknown resistance, battery, voltmeter, ammeter, plug key, rheostat, and meter scale. The only extra thing that is not in the circuit is the meter scale. Now principle, it is same as the previous experiment, Ohm's law. Ohm's law, I won't be writing the definition, I mean the statement again. Then formulas of this experiment. First formula, R, which is equals to 1 by M. That is, M is the slope, R is resistance. We get resistance by taking inverse of the slope. How we get that, I showed before. Next, the next formula we have is for resistance per unit length, as the name implies, R by L, where length we find using meter scale. Procedure, we take all the values, we plot the graph, we find the slope, then we substitute the obtained value of resistance in this equation. Finally, result, resistance per unit length of given wire, which is equals to dash ohm meter inverse. Resistivity unit is ohm meter. Resistance per unit length unit is ohm meter inverse. Okay, that's it with this experiment. Going to the third experiment. Here the diagram slightly changes. The third experiment, let's start in a new page. The third experiment is figure of merit of galvanometer. Figure of merit of galvanometer. Now, so let's do the circuit diagram first. Circuit diagram here as well, it is a little hard to draw it at first, but it is actually very simple. Circuit diagram, spelling wrong. Circuit diagram is same thing, battery first, then a resistant box system. It's not a rheostat, it is a resistance box. It has a high resistance box. Then a plug key. Plug keys here are in this experiment are very important. K1. Now in the second loop we connect a galvanometer. In the third loop we connect another resistance box. This is a shunt resistant, or like we can just call it S resistance box. One more plug key. This is the circuit where E is the potential of the battery, K1 and K2 are the switches, R and S are the resistance boxes, and G is the galvanometer. This is the only circuit diagram. Now the only thing we need in this is we need to know is EMF of the battery, or voltage or potential difference of the battery, which we normally use 2 volt, but depends, some dash volt depending on the experiment. Now, instead of explaining the tabular column right away here, let's see the aim, procedure, principle, and so on for this experiment first. This is the circuit diagram. First loop, we have a high resistance box, then switch 1. The second, we have a galvanometer. Third, it's a shunt resistance or a S resistance box. Both are resistance boxes. The apparatus of this is a battery, 2 switches or 2 plug keys, 2 resistance boxes, and a galvanometer. The aim of this experiment, to determine resistance of a galvanometer. You might be confused as the name of the experiment is figure of merit of the galvanometer, but here we are saying to determine resistance of the galvanometer. It is because to find the figure of merit of galvanometer, first we need to find the resistance of the galvanometer. We have a formula, and the formula of the resistance of galvanometer is in the formula of the uh, figure of merit of the galvanometer. So to find the figure of merit of galvanometer, we need to find the, or we need to know the resistance of the galvanometer. So to determine the resistance of the galvanometer by half deflection method, I'll explain what this half deflection method is. And to finally find its figure of merit. Okay, now apparatus, as I told, everything is in the circuit: pointer galvanometer, cell, resistance boxes, and two plug keys. Now principle is very important here. I'll show you a method which actually principle is easy to remember as well. I'll show you a method to derive one of the important formula from the principle itself. Deflection, the principle is that deflection in the galvanometer, deflection in galvanometer is directly proportional to current through the galvanometer. Which is very straightforward here. I, which is directly proportional to theta, current, which is directly proportional to deflection theta. And as we know, to remove the proportionality constant, we introduce a constant, that is figure of merit, I, which is equals to k theta. This is a main important formula. If we know this formula, we can derive the equation to solve for the main formula in this experiment. Okay, k is called the figure of merit of the galvanometer. Now formulas. K, which is equals to E by R plus G theta. This is the main formula here. So how we should get this formula, how we can get this formula is, if we remember this equation, we can get this formula without confusion, without any tension. A, which is equals to k theta, I, which is equals to k theta. We need to find figure of merit. If we shift theta this side, we will get I by theta, which is equals to k. We know from Ohm's law that I, which is equals to V by R, and in our circuit here, R, which is equals to G plus R, the total resistance, R total or R equivalent, which is equals to G plus R. So I, which is equals to V by G plus R or R plus G. So if we substitute this value here in this equation, we will get that V, or this can be written as E actually, since that is what they are using here, E by G plus R into theta, which is equals to figure of merit. I'll write in steps. Okay, I, which is equals to k theta, and again I, which is equals to E potential by resistance total, which is equals to E by resistance total, which is equals to R plus G. So if we substitute this in this equation, E by R plus G, which is equals to k theta, we need k, so k which is equals to E by r plus g theta. So from directly from this easy equation we can get our formula here, which is very important for getting the final answer in this experiment. Okay, let's continue. That is the formula. Now let's see the procedure which is important in this equation, I mean in this experiment. Procedure. First is, first step after make circuit connection as shown in the diagram. It should be exactly the same. Now second step is, let me make the circuit diagram to show it more effectively. So this is the circuit diagram. Here if we notice carefully, here this plug key is turned off, the switch is off, meaning we did not connect the plug key. It is an open plug key. Current will not flow here. So the first step is, this switch will be on. This is a battery of potential E. Now what we do is, we remove, for example, let's assume before removing any resistance from the resistance box, the galvanometer is showing some number deflection, some amount of current it's showing. It doesn't matter for us. So what we want to do here is, we need to remove R amount of resistance from R resistance box, like this resistance box, so that the galvanometer shows an even deflection, even theta. It should show an even deflection. Like for example, we should remove enough resistance in this resistance box, so that this galvanometer should show an even deflection, meaning 20, 30, 24, 26, these numbers deflection it should show. That is the first step. Now after doing that, we should note this R resistance, how much resistance we need to take from the galvanometer for it to show this much even reflection. We need to note that resistance, R amount resistance, we should note it down. Next, we close the key to plug key, meaning we add that plug key to. This is on, this plug key is on. Here I forgot to draw plug key. this plug key is also on. Now after turning on this plug key, now we take, first we took out resistance from this resistance box. Now we take out resistance from this resistance box. We take S amount of resistance from after turning on this plug key, or basically plugging this plug key, S resistance box, so that the galvanometer shows theta by 2 amount of deflection. We take, for example, in our first step, if we took out some 300 ohm of resistance here, if this galvanometer showed 30, 30 is the even number, 30 is which is equal to 30 divisions of deflection it showed. In our second step, we keep this plug key and we take out, we do not disturb the setup. Like after we take out 300 ohms from this box, just leave it like that. Do not insert them again. Now after keeping this plug key, it is still showing 30, or it might not be, but we remove some 200 ohms of resistance from this box. Now there, if it showed 30, here it should show 15 divisions of deflection. 15 divisions of deflection meaning theta by 2. Theta by 2 deflection it should show. This is just one trial, trial 1, and we should note these R and S values. The amount of resistance we took, it might be 200, 300, whatever, it depends on that specific setup. So this is the trial 1. Second trial, we take out resistance, another amount of resistance. Now let's assume it shows 20 divisions of deflection. Here in the second setup, here it should show 10 divisions of deflection. That much amount of S we should take here approximately. Okay, that's about the procedure. Now we tabulate these R and S values. Okay, like there is a tabular column here. We take different trials. 3 is the most common number. It's not working. Good. 2 curved lines. Maybe I should avoid drawing the tabular columns. It's taking too much time. Okay, trial number R, the amount of resistance we took from the first resistant box. Then deflection theta in divisions. S, the resistance we took from these second resistance box for theta by 2. This is also in ohms. Now we calculate galvanometer resistance. The formula for calculating galvanometer resistance is Rs by R minus S. And finally, K value, we don't need this line. and K value, which is equals to E by R plus G theta. This is in ampere per division. We find G value and we already have R value. This is fixed, E value is fixed. We just take numerous trials and we will get different values. Okay, the explanation is, the first thing is, let's assume I explained how we should take S and R values. This is like this theta by 2 theta deflection. If first we should take even deflection, we should remove enough resistance from this resistant box that we get a even deflection theta from here. Now in this process, this key 2 should be open, meaning this switch should be off. Now in the second step, we turn on that switch, we add the plug key here, and now we should remove enough resistance from this box so that the deflection should become theta by 2. If it was 30 in the previous one, it should become 50 here. Like that, we take numerous trials and we get numerous readings for R and S values, which we will write in our tabular column. From that, we get different G values. We calculate G using RS by R minus S formula. Here we substitute R value, S value, and we will get different G values, G1, G2, G3. And finally, we put these G1, G2, G3 values in figure of merit formula. I told you in the start why we need to calculate figure of merit in the first place is because resistance in the first place when the experiment name is figure of merit is because the figure of merit has the galvanometer resistance term in its formula, so we need to find it out. R plus G theta, this is deflection. Now actually here we should take G1 plus G2 plus G3 by 3, which is equals to average resistance of the galvanometer. This we should substitute here. Then we will get the average K value, and after doing all the calculations, we will get a result which is resistance of galvanometer, which is equals to dash ohm. After calculating figure of merit of galvanometer, which is equals to dash ampere per division. This is for the third experiment. Coming to the fourth experiment, that is voltmeter or conversion of galvanometer to voltmeter. Let's see the circuit diagram here. This circuit diagram is also simple. First battery, a switch, a rheostat, a meter, seems like I did it a little wrong. First battery, then switch, then rheostat, then galvanometer, resistance box. Now let's draw this a little different. This is a rheostat. Now we connect a voltmeter here for verification. Okay, let's understand the circuit here, why we are using this, why it needs to be like this. First of all, the battery and switch are very common, nothing to be explained there. As I explained before, this whole battery, switch and rheostat is used to adjust the voltage and current in a circuit. Voltage and current in a circuit. To adjust volt and current in a circuit, we connect a battery, a switch and a rheostat. Then that is the whole reason for this whole loop, this first loop. There is no other reason besides that. This whole thing is a single setup or a single piece or a unit which is used to adjust the voltage and current in the circuit. Now this is the main loop here, or main component. In our theory, in our textbook of fourth chapter, we saw how galvanometer can be converted into voltmeter. A galvanometer can be converted into a voltmeter by connecting a high resistance in series. Okay, that is the reason we connected an R here. A galvanometer can act as a voltmeter when we connect high resistance in it to it with in series. Now we connect a voltmeter here. The only reason for the existence of this voltmeter is to, for verification. Like for example, if this galvanometer shows after converting into a voltmeter, this galvanometer shows some 3 volt here. How we will know it is correct, accurate value or not? So to know that, we add a voltmeter. Voltmeter, we know it is connected in parallel. So we are connected in parallel. Here also, if it shows 3 volts in this voltmeter, then we know that after our experiment, we perfectly converted a galvanometer into a voltmeter. If this shows a different value, that means there is an error in our calculation or our apparatus or something is wrong. This voltmeter's purpose is only to show if our galvanometer is perfectly or accurately converted into a voltmeter or not. That is a circuit diagram. What we need for this, first we need a resistance of galvanometer, which will be given. It will be given dash ohms. 2, figure of merit of galvanometer, which will also be given. K, which is equals to dash ampere per division. Then we need to find number of divisions on either side of the galvanometer, which is represented by n, is equals to dash divisions. It is nothing much. Like if the galvanometer looks something like this, uh, In this case, the number of divisions will be 50, considering the right side or the left side, doesn't matter, just a schematic representation. In our case, in this galvanometer case, n value is equals to 50. It depends on the specific galvanometer. Okay, now fourth one, we need current required for producing full scale deflection in galvanometer. Full scale deflection of n divisions in galvanometer, which is equals to Ig, which is equals to n into k, where n is the number of divisions on either side of the galvanometer, k is the figure of merit of galvanometer, which is equals to dash ampere. And next we need a fixed voltage. For example, if we want the maximum measurement in our galvanometer to be 2 volts, then we should take that maximum voltage. Maximum voltage to be measured, which is V. We can take it as R wish 2, 3, or whatever it might be. It is a fixed value. We fix it ourselves, so don't need to worry about this. It's equals to some dash volt. Now coming to the aim, there seems to be some glitching here. Don't mind it. Aim of this experiment to convert galvanometer to ammeter, no, voltmeter of desired range. Apparatus, everything is there in the circuit itself. Principle, as I said before, galvanometer plus high resistance series gives a voltmeter, or acts as a voltmeter, as low current passes through the galvanometer. We should not write like this, as I have written it already before, and to save time I am writing like this. Now coming to the formulas. First formula, current required for full scale deflection. Current for full scale deflection, Ig, which is equals to Nk, where N is number of divisions on either side, K is figure of merit of galvanometer. 2, for the high resistance, like, okay, we understand that when we connect some high resistance in series with the galvanometer, it will act as a voltmeter. That is what we understood. But how much resistance should we connect in series with the galvanometer so that it will show accurate values of the voltage? How will we know what is R value? Don't worry about it. The manual has given us a formula. The manual has given us the formula to calculate how much resistance we should connect in series to the galvanometer. That formula I'll be writing right now. That is R, or let's write the what we are high resistance to be connected in series with the galvanometer, R, which is equals to V by Ig minus G. Okay, this is the formula. Okay, how we know like this is the actual formula? Like if it is a small formula, it is easy to remember, but if some people want to know how it is derived, I will derive it. Let's draw the circuit diagram again. Battery, switch, rheostat, galvanometer, high resistance. This is connected like this. Now let's assume this is the battery. Let's take it as V itself here, V volt. Now let's assume the current produced by this battery is I. Now consider this loop, that is, okay, before that, consider that the current passing through, okay, we need to draw the voltmeter as well. Might be better to draw. Okay, let's assume the current passing through these are connected in parallel. So if the total current produced is I, here it will be I. Okay, something wrong. Here it will be I. The current that is flowing through this branch, let's assume it as Ig. And here it is again once more I. Something wrong here. Okay, consider of this circuit diagram, I will only consider a specific loop. I'll consider this loop. It is not very correct here because the total current will not be I. It will be this. This is connected in parallel, so the total current is not same. But for understanding's sake, I draw this loop separately. This is current I. This is current Ig. The current flowing through this branch is Ig. It is different from this I current which is flowing through the whole circuit. So if we take a certain direction like this and apply KVL, loop law, Kirchhoff's loop law, if we apply that, we will get an equation. We know that the total potential difference across a closed loop is 0. So we apply KVL, we will get positive V minus Ig times G plus R which is equals to 0. From this we get G plus R. If we apply V, which is equals to IgG plus IgR, then V minus IgG, which is equals to IgR. And if you want R, which is what I was deriving the formula for, we will get V by Ig minus IgG by Ig. We will derive our formula ourselves. V by Ig minus G, which was the formula given to us. Yes, I wrote here the same formula we got using KVL. We don't need to derive it ourselves, but I did it for explanation sake or remembering sake. Now there is not much procedure here, just we take different values. After connection, we just check, like the circuit diagram is this, right? Here, after everything is done, after we calculated the R value is the main calculation part we need to do. After we remove the same amount of resistance from the resistant box, we should just find the different values of RH here. Like we should adjust the voltage and current. If this galvanometer shows 4 volts here, this voltmeter should also show 4 volts. Here, if it shows 5 volts, here the voltmeter should also show 5 volts, meaning that the galvanometer was successfully converted into a voltmeter. If we just verify that, that's enough. That's what I think so. There is no tabular column mentioned here. So the procedure explains that we should find the value of the resistance we should connect in series. We should make the circuit connections. First, we should find the R value using this formula. Then we should find Ig. How we will get to know? Ig, we will get to know Ig, which is equals to N into figure of merit. Figure of merit is already given to us. Don't need to worry about it. R equals, which is equals to V by Ig minus G. We find R. Then we make connections as seen in the circuit. Then we unplug the calculated amount of resistance from R. Like after we plug R amount of resistance from this resistance box, this galvanometer should show a full scale deflection. Normally, because there will be errors in resistance boxes apparatus and even our calculations, this will show a slightly lesser normally sometimes it will show a slightly lesser deflection than full scale deflection. So we adjust the resistance box, we plug some more resistance or something like that, and we should make this galvanometer show full scale deflection. After adjusting, R will become R dash. This R dash value also we should note down. Then finally result, the value of the calculated series resistance R, which is equals to, we will get some dash ohms, and the value of observed series resistance, this we will get as R dash, which is equals to again some dash ohms. Both should be mentioned. Okay, that's with the fourth experiment. Coming to the final experiment I'm going to be explaining in this video. That is frequency of alternating current The diagram for this experiment is very different from our previous circuit experiments. A new style diagram. There it's called a circuit diagram. Here it's just called a diagram. First, we draw an electromagnet represented by E. Then we draw a sonometer. Some wedges. A string. A pulley. Some weights. The tension here, which is equals to mass times gravitation. PQ denote the wedges. This denotes the L. L is resonating length. I don't know why it is glitching. E is an electromagnet. It is important to mention the marking here, like E is electromagnet and so on. P and Q wedges. L is resonating length. And T is tension. This is the diagram. And there is a graph for this. This is also a straight line normally. This is a graph between the square of the resonating length and tension T. Here as well we find the slope. If we consider this as ABC, slope which is equals to AB by BC. This is L square tension. What is given for us? Mass per unit length of wire, which is denoted by small m. It is given for us, which is equal to some kg meter inverse. 2, acceleration due to gravity, which is known. We take g, which is equals to 9.8 meter per second square. That is the observation or things which are given for us. There is a tabular column for this. I will write it later. Let's see the aim for this experiment. Aim to determine the frequency of AC current using a sonometer. The sonometer is basically that big board here. This is the sonometer, which has the scales, like scale, like we calculate the distance, right? That thing is called as a sonometer, and an electromagnet. apparatus, sonometer with wire, an electromagnet, slotted weights with hanger. Principle of this experiment: there are two principles here. First principle: in each cycle of AC, the sonometer string is pulled and released twice. Why that happens? Because, as we know, in an AC current, well, let's draw the graph of an AC current first. If this is a graph, that didn't come out well. This is a full cycle of an AC current. We know that, but before understanding that, what is an electromagnet? An electromagnet is when we coil around a wire around a soft magnet, or a soft, not a magnet, a soft iron core, which is, I won't explain much about it. Basically, current, we know that current produces magnetic field. Current will produce magnetic field. Normal current, it will normally go in single direction, and using right hand thumb rule, we can identify that direction of this magnetic field. We can identify the direction of the magnetic field using right hand thumb rule. But this is for direct current which is going in single direction. Even an alternating current will produce magnetic field. Due to this magnetic field, this string, which is made up of a magnetic material here, will feel a force. Normally, this force is single directional in case of a direct current. If it was a direct current, means it was a single directional, it was going to get pulled in some direction or get pushed in some direction. But because we are talking about alternating current, this is a special case. It's a special case because in an alternating current, if this was the current in against time, the alternating current will increase, then decrease, then once more increase, then decrease. So whenever it is increasing at this position, let's assume the magnetic force is acting on this magnetic string in such a way that the string is getting pulled. Now the current is decreasing. When the current is decreasing, the magnetic field is acting on the magnetic string such that it is getting pushed. Now once more, it is, the current is increasing in different direction, but still it is increasing. Once more, the string will get pulled. The magnetic field, I mean the current will once more decrease, the magnetic field will change. This time again, the string will get pushed. In a single cycle of AC, the string is getting pulled two times and pushed two times. When we play with a string, a rubber band, there will be waves in that string or vibrations in that string when we pull it or push it or just play with that kind of string. So in this case as well, due to the effect of changing magnetic field, the string is having a changing force which will get or which will make it vibrate. That is what the principle here is about. There is not much need to know about the principle, we just can remember it, but it's just the because the current is changing, the magnetic field is also changing, the direction of the magnetic field also changing. Because of that, the string is having a vibration. In each cycle of an AC, the sonometer string is pulled and released twice, causing vibration. This is the first principle. Now the second principle, we if we did this experiment before, we would have heard a condition known as resonance condition, where we begin to hear the noise or the vibration most clearly. That is known as a resonance condition. At resonance condition of this vibration, the frequency of AC is equal to half the frequency of the fundamental mode of vibration of the stretch string. We don't need to know much about it. It's just a remembering point. At resonance condition, the frequency of AC is equal to half the frequency of the fundamental mode of vibration of the stretch string. Normally, if we study the vibration or waves in a string, the fundamental mode of vibration, there is a formula for that frequency, and we, for us, we need to calculate the frequency of AC. So here the frequency of AC, which is the frequency that is basically the string is getting pulled two times, pulled and pushed two times in a single cycle, the duration of that time which in which it happens, that we equate to the half the frequency of the fundamental mode of vibration of the stretch string. There is a formula here. Principle is by hearted and formula is also by hearted. Formula: frequency of AC F, which is equals to 1 by 4 into root of mass per unit length into slope which we saw against L square, and tension slope we calculate, and here m is not slope, m is mass per unit length of the string, which is given for us already. Now procedure is nothing. I'll just draw the tabular column to explain the procedure. Trial number, which is very common in all the tabular columns. Mass attached to the string in kg. Tension in the string, tension which is equals to mass into acceleration due to gravity in newtons. Resonating length, which is L in meter, and L square in meter square. Basically, how to do this experiment is, first thing, we take different trial numbers 2, 3, 4, 5, and in the first thing is we decide a specific mass we need to attach to the string. Like we saw a hook here, right, in the diagram here. This is the diagram, this is a pulley, and here we have a hook which we can attach certain mass plates to. It can be first 1 kg, 2 kg, 3 kg, and so on. Like instead of 1 kg, normally it is more appropriate to take half kg, 0.5 kg, 1 kg, 1.5 kg, 2 kg, and 2.5 kg, and so on. And tension, we calculate, we just multiply this into 9.8 and we'll get some tension here. Resonating length is, we will understand this after we perform the experiment. Resonating length, if we see the diagram here, after we connected this electromagnet to an AC supply, and let's assume we added 0.5 kg of weight here, we will move these wedges to a certain length L, to a separation of certain length L, and we'll start to hear a sound. A very clear sound, a very large vibration will be heard. And where the vibration is very large, the wedges will be placed there. The distance between the wedges is known as, at that time, the distance between the wedges is known as resonating length. This length for different 0.5 kg, 1 kg, and so on, it will be calculated and will be tabulated. L square is then found out. Then L square and tension, we draw a graph, we find slope, we put it in the formula here. This formula is the main formula. Without this formula, this experiment cannot be done. And everything will be substituted. Finally, result, we will get it as frequency in India, we will get it as 50 hertz. The answer is already known. The frequency of AC in India, unless they gave a different source, normally it is 50 hertz, which is equals to dash hertz. I won't write 50 hertz here to avoid confusion. That's with today's video. Okay then.